All right, so I don't have the names, they're all on the table there. This was very much a group effort, although I pulled in an idea that I sort of proposed it a couple of Foresights ago, and I've been sort of only ever working on it at Foresight meetings. So the idea is what we call modular polymer catalysts. And the idea is basically to discover new catalysts that could be used in a modular way with other integrated nanosystems. And I had originally put up this idea of having these making these sort of small protein-like structures that would be like pizza wedges that would have a functional group and a surface displayed here. And we would link them together to make these sort of pizza-like shapes that would have pockets inside of them with multiple functional groups coming off of each pizza slice to assemble something like an enzyme active site in there, and then use this to discover what kind of catalysis could happen in these things. Well, last night while I was sleeping, I kept waking up, and every time I woke up, I had a vision of a smaller and smaller segment until I pared it down to just a single segment of our molecular Lego now. And okay, so what these basically are, this is like 3 or 4 of the building blocks that we make that look like this. All right, so this is one building block here. These are the bis amino acids that we build. They are linked together through pairs of amide bonds, so they're molecular Lego. Each building block has a functional group that can be chosen from any of 100 different aldehydes. So you can have metal binding groups, bulky hydrophobic groups, small alkyl groups, alcohols, whatever. Every building block has 2 stereocenters, and every one of these 6 5-membered rings is like a plate that's connected to another one through a 90-degree turn. So you make these rods, and the idea is down here we have an amino acid, so we could link these together through peptide coupling. And at the top, we would put complementary groups. In this case here, we put a dienophile and a diene that could not cross-react with each other, and in solution would not react with each other because it would be way too slow. But if you link one of these segments to another segment, then these two are held close enough together, and it's sort of like mechanosynthesis. They're close enough, the concentration is really high relative to each other, and they would cross-react in a few minutes. And we could promote that with heat. Okay, so here's the idea. We attach one of these segments with different functional groups on it. We make like 50 of them. We attach one of them that's been capped on this side so that it doesn't react with any, it'll be sort of dead. We attach one segment, we take off the protecting group, we have a free amine, we bring in another whole segment, this is like 1 kilodalton, and it attaches to there, and we link these two through an amide bond. We could put additional amino acids in here if we want to stretch it out a little bit, but once they're linked together, now these two are close enough together that they would cross-react in a reasonable amount of time if we heat them, and they would cyclize and make a macrocycle. So that's like 2 segments linked together like this. Then we do it again and again and again. We do it 5, 6 times, and we create something like this. It's like a foldable fence. It's got functional groups sticking out of this surface, sticking out of this surface, and the sorts of groups that we would go after. Well, let me back up. I've actually gotten out of order of what I was going to talk about, but here's what we're trying to do. We're trying to assemble enzyme-like pockets from modules. These are the modules. The benefits, these molecules will hold together their shape in any solvent. You could use them in any organic solvents, water, any solvent you want. They would work at high temperature because they're not going to unfold like proteins. They are these sort of fence-like structures. Their size is intermediate between like small molecule drugs. They're about 5 kilodaltons. Small molecules are about 500 daltons. Proteins are, 50,000. They're much higher. So these are smallish, medium-sized molecules, and we could put a lot of diverse functional groups hanging off of these segments to bind metals and create catalytic sites. Once we throw in a metal and it curls up around it and it creates a little pocket inside of it. Now, okay, so we would be able to put all sorts of diverse functional groups on it. So there's an advantage. These are some of the advantages over, doing this with like proteins, for instance. The other advantage is that these would be immune to proteases. They'd be invisible to the immune system. You could use them as catalysts that would be drugs. So catalysts, you can in principle make a catalyst that would like reverse the Maillard reaction, and you would have something that would get rid of wrinkles because it could work its way into the extracellular matrix that's been all cross-linked with aging and reverse those chemical reactions and loosen up the extracellular matrix. Protein enzymes would not be able to get in there because they'd be 10, 20, 30 times too larger than that. Our initial targets would be metalloenzymes because what we could do is present metal binding groups on a couple of these units, and when you throw in the metal, it'll close up around it, creating those metal ligand interactions and create a pocket wherein catalysis will happen. The goal is ultimately to do catalysis by design and to create small catalysts that could then be incorporated into all your other systems in a way where you could switch those catalysts off and on. So if you pull them open, they stop working. You let them close up, they do their function. So it would be switchable catalysis, like what we see in all sorts of DNA polymerases, all sorts of biological machinery. It's all about catalysis that's switched on and off at the right time. So that's something that we could get from this. And they're small, and you could functionalize the back end to interact with whatever system you have, and it wouldn't change what's going on this side, so you would still retain the catalytic function while being able to put it onto anything you want. Okay, so you could integrate them into other nanosystems. They'd be switchable. And okay, so here's how we would make them. We would make them using positional assembly. So basically, a 2 centimeter by 2 centimeter pad would have these little 1 millimeter by 1 millimeter pixels on them that would be activated with a free amine so that you could link the first unit on here. And you would be able to spot one, if you have 100 different segments, you could spot the first one here, the second one there, third one there, so on a grid, and then take off all the protecting groups in one step, and then put the second one here, the 9th one there, the first one there, and build up a different sequence on every pixel. So if you have 1,000 by 1,000 pixels, that's a 2 centimeter by 2 centimeter chip, you have 1 million different potential catalysts organized on this thing. You can flow substrate over it by bringing in, there's a couple of ways to detect if there's activity. One would be if you generate fluorescent products, you would detect it by fluorescence over the pixel. So you could also use thermal cameras to detect the heat evolved. You could also bring in a sipper and suck up the products and run them into a mass spec. What you learn about which catalysts work, you could then use to make another round of catalysts that are focused in to make a better catalyst.
So one question from the judges here. Then
in silico discovery, you're going to take a bunch of different catalysts and one substrate to put products together.
And then, and then flow the next substrate over it. So you could flow hundreds of over one chip.
Great. And I think it's also important that it doesn't always have to be a barrel. By changing how it's binding the metal on the R groups, you're going to be able to create triangles and slightly different shapes that might better accommodate some of these. And we had some theory over here too.
All right, thank you so much.
Thank you.